Welcome back to another episode of Dave Does Math from Home. We are still talking about maximum and minimums. This is section 4.1. We're doing part 2 of this section now. In part 1, the summary of part 1 is we're finding maximums and minimums of analytic functions by finding all the critical points, which is where the derivative equals 0. It's where the slope of the tangent line is flat. We find the critical points and we look at the endpoints. We evaluate the function at all of those points to find where you get the largest y value and where you get the smallest y value, and that's how we identify the maximum and the minimum for that function on that range. So I have another example for us to work on right now. This is x plus 14 to the 2/3 power, so a horizontally shifted power function on the interval from -15 to +13. This is what we're going to work with. And as usual, we're going to start by finding a derivative so we can get our critical points. F prime of x equals, bring the exponent down, so 2/3 x plus 14 to the -1/3, which is also known as 2/3 cube roots of x plus 14. So, easy derivative, messy simplification if you want to use a radical. But this is our derivative. And we need to set this equal to 0. And as we all know from our work in pre-calculus, if we want a fraction or a rational expression to be equal to 0, we need to set the numerator equal to 0, which you can also accomplish by multiplying both sides of this equation by the denominator. And that would give you 2 equals 0. And hopefully we can all recognize that this has no solutions. This is no good. So what do we do when there's no critical points? I'm glad you asked, hypothetical viewer who I'm engaging in hypothetical dialogue with. The answer is, well, the answer to that question as asked is, if there's no critical points, then don't worry about it. If there's no critical points, use the endpoints. You can still get a maximum and a minimum out of some endpoints. That's if there are no critical points. This problem is kind of a trick question though, and it's a trick question because I have lied to you by omission. I said critical points are where the derivative equals 0. And that's true about 90% of the time, 95% of the time, critical points happen when the derivative equals 0. But there's also sort of like a special niche case that we need to talk about for when weird stuff happens. Critical points can also happen when the derivative is undefined. So that's what this example is going to illustrate for us. We need to look at where the derivative is 0, but we also need to look at where the derivative is possibly undefined. This wasn't a concern in the last two problems, because in the last two problems we were dealing with polynomials. And polynomials are, as we know, well-behaved, smooth, continuous, they're nice, they don't have domain restrictions. Polynomials are never undefined, which is why we like them so much. This has the potential to be undefined. We have variables in denominators. This could be a problem. If x equals -14, then this is the cube root of 0, and that puts 0 in the denominator, so x equals -14 is our critical point. And x equals -15, and +13 are our endpoints. So, again, sometimes you'll end up in situations where there aren't any critical points. That happens with, I'll take a quick break from this, that happens with stuff like f of x equals e to the x. The derivative is e to the x, which, again, we remember from pre-calculus, this is never equal to 0, and it's never undefined. F of x equals e to the x has no critical points. Derivative is always positive. It's never 0, never undefined. And in this case, that's fine. We can just, if we are doing something with an e to the x, we just look at the endpoints, you figure out your maximum and your minimum, based on your endpoints. That's not a problem. But sometimes, when you're dealing with things that aren't polynomials, you also need to consider where the derivative is undefined, which usually means you're going to end up trying to make a division by zero error happen. So our division by zero error happens when x is negative 14, so that's a critical point. We need to be careful about that. It's also interesting to note that x equals negative 14 makes the derivative undefined. Well, let's see what happens when we plug it into the original function. F of negative 14 is 0 to the 2/3, and that's just 0. And that's fine. So the derivative is undefined, but the original function has a value. Let's look at f of negative 15. When we plug negative 15 in here, we have negative 1 to the 2/3. And that's just, so negative 1 squared is positive 1. The cube root of positive 1 is 1. And f of positive 13 will give us 27 to the 2/3, which is, cube root of 27 is 3, squared should be 9. So I have a maximum at 9, and I have a minimum, I'm sorry, the maximum is 9, and it's at x equals 13. And my minimum is 0, which occurs at x equals negative 14. So the minimum is coming from my critical points, and the maximum is coming from one of my endpoints. This function looks like this. Graphically, this thing right here is called a cusp, where the graph comes to a sharp point. There's no tangent line at this sharp point. Infinitely many different lines are all tangent to the function at a point, at a sharp point like that. You only get single, uniquely defined tangent lines. Like, when you have a function that's smooth, it gives you a unique tangent line. There's only one line that's tangent to the function at this point. There's infinitely many that are tangent here, because it's a sharp point, it's not smooth. That's why the derivative is undefined, and that sharp pointiness is why we need to consider these things as potential critical points. So this has been our critical point example. Most of the problems we're going to see are not really going to look like this. They're going to be more well-behaved. But this is a good thing to have experienced, so that you know for sure how to find these critical points. That'll do it for this section of videos on section 4.1. We're going to pick up with section 4.3. We're skipping 4.2. I don't even remember what 4.2 is, but it's not important. We're going to pick up with 4.3 real soon. It follows, like I said, we're going to slide into that. It's going to be a real smooth transition. In 4.3, we're going to do almost exactly the same things. We're just going to take away these bounds. Because in 4.3, we don't care about global max and global min. We're not looking for the very biggest thing there is and the very smallest thing there is. We're going to look for all of the local extrema. So we want to categorize all of the critical points that something has as either local maximums or local minimums. And we'll talk about some techniques to do that in 4.3. I'm going to wrap this one up for 4.1. We'll see you next time.